In this example problem, we're going to design a beam to span 46 feet, and we're going to assume that this is a building design. We're going to use a beam with a 10-foot width. So you can see our center to center, our span length for our beam is 46 feet here, and we have 4-inch bearings that come up to the end of the beam on each end. We're given some initial properties for our concrete, so we're going to start assuming that we have a release strength of 3.5 KSI and an ultimate strength of 5 KSI. We're going to use a 1/2-inch diameter low relaxation strands, and we're given some details about our loading. So we have an applied live load of 50 pounds per square foot and a superimposed dead load of 15 pounds per square foot. So our total superimposed load is going to be 50 plus 15 or 65 pounds per square foot applied over that 10-foot width of the beam. And here's some information for our strands. We have 270 KSI strands, and we're stressing them to 75% of the ultimate strength. I give us here the release modulus and the modulus at service for our concrete using our ACI 318 equations. Our first step is to choose a cross-section that is appropriate for our span length and given loading. There are a number of different design aids that we can use. I'm giving us one from Collins and Mitchell, where we have our superimposed service load on the y-axis and the span length on the x. And this just helps us to know what kind of cross-section that we would need. Essentially, hollow core and double T's are the main two sections that are used, so we can decide between these two using this chart. You can see here with our 65 pounds per square foot superimposed service load and 46-foot span length, we're right here, kind of just outside the length for hollow core slab, so we're going to use a double T section. If you're doing a precast building design, you're going to use the PCI design handbook. And chapter 3 has some information on preliminary design, and it has a number of different design tables for some of the standard precast concrete sections. We're going to use a pre-topped double T section with no cast in place composite topping. So you can see the top of this design chart has some information on our section, the top flange width we'll need, the total depth, the thickness of our top flange, and then we have some standard section properties for this 10DT26 section. So you can see we have our gross section properties, the weight, and our volume to surface area ratio, which we'll need for our creep and shrinkage equations. So you can see here also, it gives us a design table that allows us to go in with our safe superimposed service load. So we had 65 pounds per square foot, so we'd be right there with a 46-foot span. And with this, we can come and see a strand pattern and whether we need straight or draped strands, the diameter of the strand, and the number of the strands. So if we had 8 1/2-inch diameter strands with a straight strand pattern with a centroid of the strand equal to 5 inches, the design table would say that we should be able to resist up to 67 pounds per square foot for a 46-foot span. So we have this information and we'll have it in the back of our mind throughout this example, but we're going to move forward like we don't have this design table. So on the next couple slides, we'll go through what's called the kern point analysis for figuring out the number of strands and strand location. The first step in our kern point analysis is to determine our demand along the length. So here we have our given loading. We have our self-weight moment, our superimposed dead load, and our live load. You can see I'm taking our pressure load times the 10-foot top flange width to get the distributed load that will apply to our simply supported beam. So for our superimposed dead load, we'll have 150 pounds per foot, and for our live load, we'll have a distributed load of 500 pounds per foot. We can find our unfactored service moment just by adding our distributed loads together. We have a simply supported beam, so the maximum midspan moment will be WL squared over 8. So we can calculate those values there. And then our factored moment, we're going to use the ACI 318 load factors. 1.2 times our dead loads plus 1.6 times our live load gives us our total factored distributed load. So we take that W times our L squared over 8 to get our factored moment at midspan. Next, we need to have some approximate equations here for our eccentricity plus our top kern point. So we have a double T section, so we'll use this 0.7 times h. But if you have another cross-section shape, you can just choose the appropriate value from the tables that I'm showing here, which are from the Collins and Mitchell textbook. So here, using the double T cross-section shape and the approximate E plus KT value of 0.7h, we can find an E plus KT of 18.2 inches. And we need to find our stress limit for the uncracked member at bottom fiber stress, which is just 7.5 times our square root of F prime C, which gives us 0.53 KSI. And then we can plug these values into our approximate minimum pre-stressing equation. And again, this is from our kern point analysis. So for more details about the derivation for the kern point equations, you can go to the presentation video for this module. But you can see here, using the approximate equation, we would get that we need a total pre-stressing force greater than or equal to 194.4 kips. We need to assume an effective pre-stress after all losses, which we're going to assume 25% total losses, which is a reasonable assumption. And it might be less than this. We'll calculate it when we're analyzing the actual section. But here we can see a value here of 151.9 KSI. So taking our total force divided by our approximate effective pre-stress will give us the approximate required pre-stressing area. You can see here, we need a pre-stressing greater than 1.28 square inches. So we're kind of right above where we would be for eight strands. You can see we may have overestimated our losses. So using 8 strands is probably okay, but we're going to go forward and use 10 strands in this example. And note that the PCI design handbook suggests using 8 strands. So we'd be okay moving forward and checking to see if 8 strands would work. On the next few slides, we're going to determine our tendon profile using our kern point equations. What we're going to do is we're going to find a minimum eccentricity at the ends and at midspan, and a maximum eccentricity at the ends and midspan. And then we're going to see if we can use a straight strand profile so we can have our strands within these bounds. If we can't, then we either need to debond the strands at the end, or harp our strands, or increase the strength of our concrete, and that'll change where the upper and lower limits are. The first part is finding our minimum and maximum eccentricity at the ends of the member. And to do this, we need to figure out our allowable tension stress at the ends of the member at release, which is 6 times the square root of F prime CI, so our release strength of the concrete for ACI. And we need our transfer length for the strand. So we're going to assume initially, since we don't know our F sub CI, that our transfer length is about equal to 50 times the diameter of the strand, or 25 inches. We can then find our bottom kern point here. So KB is our section modulus at the top divided by our AG. So here will be 7.8 inches. We'll need to find our minimum moment, and we're looking at the end of the member, or here at transfer length. So the minimum moment is going to be, we can plug in our self weight into this equation and get our min moment of 364 kip inches. And our pre-stressing force is just our stress after elastic shortening, with which we estimated on the previous slide, times the total area of our pre-stressing. So we have our 10 strands. And then that'll give us our total pre-stress force here of 291.2 kips. We plug all these values into our max eccentricity equation, and we can see that our max eccentricity at the ends of the member, or at the transfer length, are equal to 15.6 inches. So we need to make sure that our eccentricity is less than this value at the ends of the member. Our next step is to find the minimum eccentricity at the transfer length. And this minimum eccentricity is going to be controlled by the tensile stress at the bottom of the beam at service. So here we have our our current point equation for our minimum eccentricity, and we need to calculate some of these different values. So our top current point equation here, just our section modulus to the bottom divided by our gross area, gives us 2.2 inches. And our maximum moment at the transfer length, including all of our service loads, is going to be 693.4 kip inches. We can find the final pre-stressing force by taking our total area times our effective pre-stress, the stress in the pre-stressing after all of our pre-stress losses, which we had assumed a few slides ago. And we'll get a total pre-stressing force of 232.4 kips. Our allowable tensile stress is the same as we found before. Our ACI 318 limit for an uncracked section is 7.5 times our square root of F prime C, 530 PSI or 0.53 KSI. We can plug all these values into our minimum eccentricity equation here and see that we have a minimum eccentricity of negative 2.7 inches. So this is 2.7 inches above the centroid of our section. So here then you can see the range of eccentricities where we need to keep our strands to meet our primary stress checks. So our minimum eccentricity of negative 2.7 inches and our maximum eccentricity of 15.6 inches. So as long as we keep our strands between these values in at the transfer region or at the ends of the beam, we'll most likely meet our stress checks at that location. Next, we need to do the same thing at the midspan of the member. So we can go through again to find our maximum eccentricity limit and find our allowable tensile stress and our bottom current point using the equations shown here. Next, we need to find our minimum moment at midspan using just our WL squared over 8 equation with our self-weight distributed load, and our pre-stressing force, which is the same as we found before. Plugging all these values into our maximum eccentricity limit gives us a value here of 18.9 inches. Next, we need to find our minimum eccentricity, and we'll use the same equation that we did before, only we'll use our values at midspan. So our top current point stays the same. Our maximum moment increases because at midspan we have WL squared over 8 using all of our distributed service loads. Our pre-stressing force is going to be the same as we had before. Our allowable tension is the same as at the transfer length. So plugging all these values in, we can get a minimum eccentricity here of 13.0 inches. The current point analyses give us the range of eccentricities at the midspan and also the range at the ends or at the transfer length. So you can see as long as we keep the centroid of the strands between the minimum and maximum eccentricities at the midspan and at transfer length, we most likely will meet our stress checks. So you can see we have a range here between the minimum eccentricity at the midspan and maximum eccentricity at the ends of the member, where we can use a straight strand profile. So as long as we stay between 13.0 and 15.6 inches, we will most likely meet our stress checks at midspan and at the ends. You can see here an assumed possible strand location pattern for our double T sections. We're assuming that we have a 2 inch by 2 inch grid with a possible location of 2 strands side by side in each web. And what we're going to try here is we're going to try no strands in the bottom layer, and then 4 strands in the second layer, 4 strands in the third layer, and 2 strands in the fourth layer. So you can see the number of strands and the height of each strand. We can calculate the centroid of our strands just by using a weighted average. Because all of our strands have the same area, we can just take the number of strands times the height of that layer of strands, and then sum all of our different components. So we have our 3 layers of strands here, 4 times 4 inches, 4 times 6 inches, 2 times 8 inches, and then divide by the total number of strands, 10. So that gives us a centroid here of 5.6, and we can take the YB minus the YP to get our eccentricity here, 14.7 inches. This 14.7 falls between our min and max eccentricity, as I talked about above. So we assume that if we use this strand pattern, all of our stresses will check, although we do need to actually check the stresses when we analyze the section, which we'll do on the next couple slides. At this point, we're transitioning from the design process to the analysis process. So typically what I want you to do and what I'll do is I'll draw the actual section that we'll be analyzing. So here's our section with our centroid of our strands, the total area of our strands, and the material properties that will start off with our analysis when we're checking our different design limits. The different ACI 318-19 stress limits are shown on this slide. We need to check our stresses at release, and we also need to check our stresses at service. And our stress limits at release are dependent on if we're in compression or tension, and if we're looking at the ends of the simply supported member or other locations along the length. Typically, the end of the member is considered within the transfer length, so that's what we'll use in this example. The stress limits at service are dependent on whether we're compression or tension again, and then the type of load that we have. So here, if we're looking at the pre-stressed plus sustained loads, our compression limit is a 0.45 F prime C, compared to if we're looking at pre-stress plus total loads, we have 0.6 times F prime C, and a tensile stress limit of 7.5 times the square root of F prime C, which will keep our beam an uncracked beam, a class U beam. So here are our stress limits again. Next, we need to calculate our actual pre-stress losses for the section that we're analyzing. So we're going to use the PCI Design Handbook approach, which is the approach that you'll typically use for building members. And this approach, we calculate an elastic shortening loss and then a creep, shrinkage, and relaxation loss. So I'm not going to go through this in too much detail. We've covered it in previous examples, but I'd provide it here for you so you can look through it if this is new to you. So we can calculate our elastic shortening loss, which we find to be 10.8 inches, and we'll go through and calculate our required values for our creep loss. And we can plug these values into our creep loss equation to get a total creep loss here of 14.8 KSI. And then we can calculate our shrinkage loss using our volume to surface area ratio, which was given for our specific section in the PCI Design Handbook, and the relative humidity, which is also given here as 70%. And then plug these values into our shrinkage strain and then shrinkage loss equation to get a total shrinkage loss of 6.1 KSI. Finally, we need to calculate our relaxation loss. And to do that, we'll need to find some of our constant coefficients here. So we have grade 270 low relaxation strands, which are the typical strand used. So we'll have a K relaxation equal to 5,000 PSI and a J equal to 0.04. Our C value, we were given that our initial pre-stress is 75% of our ultimate stress in the strand, so we have a C equal to 1. So we can get those constants as shown here. Plugging all of our values into our relaxation equation, we can find a total relaxation loss of 3.7 KSI. And then we can add together all of our different losses here to get our total pre-stress loss of 35.5 KSI. We'll need the force after transfer and the force at service in our stress calculations, so that's what I'm finding here. The force after transfer considers the stress after elastic shortening times our total area, and the stress at service is our stress, or our service stress after all pre-stress losses times our area. So we have those two values there, force after transfer and force at service. After we calculate our pre-stress losses, we're ready to check our stresses at release, under sustained loads, and service loads. We're going to use the force in the tendon approach to calculate our stresses, and we'll find them at the top fiber and bottom fiber in our precast section using the equations shown here. Note that negative is compression and positive is tension in these equations. So you can see, plugging our different values, at the transfer length, we can calculate the top fiber stress, and we'll find our top fiber to be 0.294 KSI in tension. We can compare this to our tensile stress limit at release at the transfer length of 6 times the square root of F prime CI of which will give us a tensile stress limit of 0.355. So we can see our stresses are okay here. Next, we can find our bottom fiber stress at the same location, and we can find we'll have a compression stress of around -3 KSI. This is greater than our compression stress limit at the transfer length at release of 0.7 times F prime CI. So this is no good. So our stresses don't check at release, so we need to change our design somehow. Some different options that we could try. We could try decreasing the number of strands. You know, we know we tried 10 strands and we thought 8 strands might work, so we could try decreasing to 8 strands. Decreasing the number of strands would decrease our compression, which will decrease our compression stress here. We could try debonding some of the strands in the end region. So if we debond, we're also decreasing the force in the strands at the transfer length, so we decrease the compression here as well. Or we can try increasing our concrete release strength, and doing this would increase the stress limits here. So we're going to try increasing our concrete strength. It's the most expensive option, but it'll be the easiest option for us to work with in this example. So we're going to try increasing our concrete release strength to 6 KSI, and if we increase the release strength, typically it's also going to increase the ultimate strength. So we're going to move forward with an ultimate strength of 8 KSI in this example. Changing the concrete strength is going to change our pre-stress losses, so we'll need to recalculate them. I don't give you all the equations here, but I give you the final losses. So if you wanted to check yourself, you could go back and use the PCI equations and you should get these same pre-stress losses. So we'll get an elastic shortening loss of 8.2 KSI, a total pre-stress loss of 30 KSI, and you can see the corresponding force after transfer and force at service. So you can check the stresses along the length of the beam here. The orange here is the stress in the top fiber, and the green is the stress in the bottom fiber. And we can compare these to the tension and compression limits in the section. And we can see that our top fiber tensile stress stays within our tension limits, and our bottom fiber compression stays within our compression limits. So our stresses now check at release. Next, we can check our stresses from all of our sustained loads. When we're looking at our sustained loads, we're looking at final time. So we're going to look at we're going to use the force in the pre-stressing after all of our pre-stress losses are taken off. And we're going to also include all of our sustained loads when calculating our flexural stress from applied loads. So we have our self-weight moment and our superimposed dead load moments. So plugging in all of our different values here, we can see that we have tension in the top fiber, which is less than our tension limit, so we're okay there. There aren't any tensile stress limits for the sustained loads, but we still should check it against the tensile limit under all service loads. So we're okay there. The bottom fiber stress, we have a sustained stress equal to about -2.6, so 2.6 KSI compression. We can compare that to our sustained, or our stress limit for our sustained load, and we can see that we're okay here. We need to check it along the length, which is what I do in this figure, and we can see that all of our compression stress stays below the compression limit as shown. The last set of stresses that we need to check are our stresses from all of our total loads. So you can see we're still looking at final time, so we're still using P sub F, but now we include our self-weight moment, our superimposed dead load moment, and our live load moment. Because we're using gross section properties with the force on the tendon approach, we can combine all of our moments together to get a total moment here. So our top fiber stress at midspan, which will typically control for us when we're looking at our stresses from our total loads. We can find the the stress at the top fiber stress, we're going to have about negative 4.7 KSI. So we'll have a compressive stress at the top fiber. And we're also going to have a compression or compressive stress in the bottom fiber here. So you can see we stay within our compression and tension stress limits. So typically, the stress at midspan at the bottom of the section is going to be in tension if we allow it to be in tension. And this limit here, the tensile stress limit, 7.5 times the square root of F prime C, is going to control the design. So you can see we have a lot of space, a lot of room here between the bottom fiber stress and our tension limit. So this would again suggest that we could possibly try getting rid of some strands. Our next step is to check our flexural capacity. And we need to make sure that our factored capacity is greater than our ultimate moment. So we'll use the procedure that we went over in Module 8, which is the rectangular stress block approach. So we need to make sure that our rectangular stress block here with a width of B, so the whole top flange width, and we'll need to check to make sure that it stays within the top flange section. So here we can calculate our beta 1 factor. So our beta 1 for 8 KSI is going to be 0.65. We need our pre-stressing ratio, which is our total pre-stress area divided by B, the width of our compression face, which is here 10 feet or 120 inches, times D sub P, the distance between the compression face and the centroid of all your strands, 20.4 inches. So we have a pre-stressing ratio here. And we can plug these values into our F sub PS equation, where we have a gamma P sub factor of 0.28 here, which is will be typical for our pre-tension sections. So we can get an FPS here of 267.5 KSI. We can look at our equilibrium expression here with no externally applied loads. So set tension equal to compression and solve for our compression block depth, and we'll get a depth here of 0.5 inches. We can see that this 0.5 is less than the top flange thickness of 4 inches. So we know that our compression block is still within the top flange. This will be typical for most of our sections since we have such a large or wide top flange. Next, we can calculate our neutral axis depth by just taking our A divided by beta 1, and we can use this C to find the strain in our pre-stressing, assuming a linear strain profile. So we'll find a strain here equal to this value, 0.076. And we can compare that to our tension control limit, which we found in the previous module for pre-stress sections is going to be 0.005. Because we're tension controlled, we can use a phi of 0.9. Our flexural strength we can find just by summing moments about the centroid of our compression block. So we have tension, our tension force, so pre-stressing area times the stress in the pre-stress, times the lever arm between the centroid of the compression block and the centroid of our tension force. So D minus A over 2, and we'll get our nominal moment here. We take that nominal moment times 0.9 to get phi mn, and we can compare that to the ultimate moment at midspan, which we found earlier to be 5,844 kip inches. So we can see we're okay here for the flexural capacity. And we can calculate a safety index here just to see how much over strength or how much extra strength we have in the section. And we can see we have a safety index of 1.27. Typically the safety index, if we're around 20% or 10 or 20%, that's okay. If we're way above 20% or above 30%, then we're over designed and we can try removing some strands. We need to check the flexural capacity along the length of the beam, and to do this we'll need to calculate our transfer length and our development length. So these are the required lengths to be able to transfer the effective pre-stress into the strand and develop the ultimate stress in the pre-stressing in the strand. So you can see we get these values here, a required development length of 76.3 and a required transfer length of 28.7 inches. If we have an available development length at the section where we're checking the moment capacity, if we have an available development length less than the required, then we're going to have a smaller stress in the pre-stressing. And we can calculate that stress in the pre-stressing using these equations here. Using the equations that we have looked at on the previous couple slides, including the reduced stress in the strand due to transfer and development length equations, we'll get a factored resistance along the length shown in blue and an ultimate demand shown in the dotted red. So you can see the blue encompasses the dotted red, so along the length our beam has sufficient flexural capacity. You can see we do have some extra capacity here, so again this would suggest that we can try getting rid of some strands. Our next step is to check the reserve strength after cracking, and we'll do this using this ACI 31819 requirement. The requirement says that we need to develop a design moment strength at least 1.2 times the cracking moment strength. So we need to make sure that our Φmn is greater than or equal to 1.2 times MCR. What this limit does is it ensures that we have some ductility in our section. It helps us to make sure that our beam doesn't immediately fail after it cracks. Our pre-stress members we designed to have a much higher cracking moment than typical reinforced concrete members, so this limit will sometimes control our design. We can calculate some of our required section properties. Our section modulus, our rupture strength of our concrete, 7.5 times square root F prime C, the pre-stress force at service after all of our pre-stress losses, and then we can calculate the stress at the bottom fiber, so F sub CB, using our force in the tendon equation, and set it equal to the tensile strength of our concrete, or the rupture strength. Our M sub CR is our cracking moment is going to be our only unknown, so we can solve for MCR and then plug in all of our known values, and we'll get a cracking moment here equal to 5,472 kip inches. We can compare this, or take this times 1.2 and compare that value to our Φmn and see that in this case our code equation checks. Our final step here is to check our deflections. And we're going to check our deflections using the PCI multiplier approach. With this approach, we calculate 4 base deflections, and then we use multipliers to take into account creep, shrinkage, and strain relaxation. So you can see we'll calculate these different deflections, and then we'll compare them against our different ACI 318 deflection limits. We need to check to make sure that our immediate deflection from our live load only is less than L over 360. And then we'll also need to check to make sure that our deflection after the attachment of non-structural elements is less than L over 240. And we'll use these equations here from PCI to check those limits. We'll need to calculate the concrete modulus at release and ultimate with our new concrete strengths. So I'd give that to us here using our ACI 31819 equations. If we assume linear elastic material properties, we can calculate our 4 different base equations as shown on this slide. And when we're calculating our base deflection due to pre-stressing and self-weight, we'll use our modulus at release. When we're calculating our base deflections due to our superimposed dead loads and live loads, we'll use the modulus at ultimate. So you can see plugging in these different values, we have a pre-stress deflection of negative 1.23 inches. So this is my sign convention means it's an upward deflection. Our self-weight deflection is 0.53 inches down. Superimposed dead load, 0.1 inch down, and our live load deflection, 0.32 inches down. We can then use these deflections with our different PCI multipliers to find our different deflections at different times. The couple deflections that we'll need for our code equation checks are shown here. We'll need to find our camber at time of erection and our final camber. So using our base deflections times our moment magnifiers, we can find our camber at erection of negative 1.12 inch upward and our final camber of negative 1.28 inches upward. And then we can check our code limits. Our live load deflection we found to be 0.32 inches, which is less than L over 360, which is equal to 1.53 inches. So we're okay here with that limit check. The second one, the deflection after the attachment of non-structural elements, we can plug in our values into this left equation and find a deflection here of 0.47 inches. Compare that to L over 240, which is 2.3 inches, and see that our deflection's okay there as well. So this section meets all of our deflection limit checks. That concludes this flexural design example. Our final section that we designed for Flexure and checked against all of our flexural limits from ACI 318 is shown here. So we have a total strand area. We have 10 half-inch diameter strands with a centroid equal to 5.6 inches or square inches. And we're using concrete with a 6 KSI release strength and 8 KSI ultimate strength. We checked our tension and compression stress limits in the concrete at release due to sustained loads and due to service loads along the length of the beam. We checked the flexural strength of the member along the length of the beam. We checked the reserve capacity after cracking to make sure our beam doesn't crack and immediately fail. And we checked our deflection limits. We're going to check shear we're going to learn about shear in a later module, so we're not including that in this design example. On a side note, we could optimize our section. I've mentioned it several times that we could look into using 8 strands rather than 10. We could indeed use 8 strands in the section with this strand profile and with the original concrete strength that we had, and we would meet all of our different design checks. Note again that this is a design problem, so there isn't just one right solution. You can have many different strand patterns, you could use different section shapes and different concrete strengths and still meet all of our design checks. So there is a lot of flexibility in the design process. With that, this concludes this design example.